All right, let's take on problem 4, and as it says in problem 4, let's use the p-value approach. And I'm gonna tell you that the p-value approach is significantly simpler from an operational point of view than the traditional approach that we've been using, and you'll see that in just a moment here. So let me read the problem and let's move on from there. It says, boys of a certain age are known to have a mean weight of 85 pounds. A complaint is made that boys living in a municipal children's home are underfed, in which case you'd expect them to weigh less than 85 pounds, right? As one bit of evidence, 25 boys of the same age are weighed and found to have a mean weight, X bar, of 80.94 pounds. It's known that the population standard deviation is 11.6 pounds. Based on the available data, what should be concluded concerning the complaint? So if we were going to do this through traditional method, we'd state the null and alternative hypotheses. We'd pick whether or not this is a right, left, or two-tailed. We'd calculate a test statistic and a critical value, lines in the sand and a test statistic, and we'd compare the two to see if our test statistic fell in the critical region or in the non-critical region. So the p-value, you do just about the same thing. It's really just changing a point of view. But rather than comparing values along the x-axis or the z-axis, we're just going to compare areas. Because the areas, remember, are probabilities. And the first probability is alpha itself, the significance level. Remember, that's the probability of making a type 1 error. So you set that low. You don't want to make a type 1 error. So you set the probabilities out in the wings low. And in alpha itself is an area and therefore is a probability. So in this particular problem, alpha is not specified. So no problem. You know what to do then. You pick 5% as alpha. And then we're going to calculate a p-value, which is, get this, the probability associated with the sample, the 80.94. What's the probability that we would reach into the sampling distribution associated with this problem and pull out 80.94? We have said beforehand, if we're 5% or less, that 80.94 is an unusual, statistically significant number. We should pay attention to it. We will even reject the null when we see it. That occurs when the p-value is less than alpha. Otherwise, if the p-value is greater than alpha, not unusual. Any difference, 80.94 versus 85, is sampling error. So let's do this real quick. What is the null hypothesis? Mu is equal to 85. What is the alternative hypothesis? Mu is less than 85. Yeah, that makes this a left-tailed test. And we're going to just write down alpha is equal to 0.4. So right there, we have written down the null hypothesis, written down the significance level, important to do here. We recognize this is left tail, and we draw our little picture and show ourselves the critical area. It is the area in the tail that has an area under the curve of 0.05. So now what do we want? All we want to do, we don't have to calculate z-test, we don't have to calculate z-crit. Instead, we're going to calculate the p-value, which is the probability of pulling out 80.94 or an even more extreme number. That's the area under the curve from minus infinity up to 80.94. That is normal CDF. Normal CDF with the lower bound minus E99 or minus 9 nines or 6 nines. The upper bound 80.94. The mean of the sampling distribution is 85, and the standard deviation of the sampling distribution is 11.6 divided by the square root of n, and n is 25. When you work that out, normal CDF tells you that the p-value is 0.04. Okay, so we've got 0.04 drawn there, And the area under the curve to the left of that red line is the p-value. And note that it is less than, it is an even more extreme result than alpha is. And we've said alpha is where we're going to essentially draw our line in the sand. We're going to assume that any probability less than 5% is unusual. And here it is, a probability less than 5%. In fact, it's 4%. So to make the decision, p is less than alpha, so the sample result, 80.94, is even more improbable than the chosen level of significance, and therefore you reject null. Much easier, huh? We didn't have to calculate a z-test. We didn't have to calculate a critical value. We just compared p, which we get from normal CDF, to alpha, which we are given in the problem statement, or if we're not, as in this case, we say is 0.05. Okay, let's move on.